All right, so this video will be an introduction to Riemann sums, which are thought of as, well, for us, it's going to be four different kinds. We got right, we got left, we got midpoint approximations, and we also have trapezoids that we'll do in a later video. So to start this off, they've given us an example here. This number one, it says use five right-hand rectangles to approximate this integral right over here from 0 to 10 at 3x squared plus 2. So first thing I want to do on this, notice we get to use a calculator. We already know kind of what this graph looks like, so I'm just going to do a quick, real simple picture over here. We know it's a parabola, and we know it, let's see, it crosses the y-axis at 2. Maybe that's like right here, and it's opening up, so it's going to look something like that. We know it's a parabola. We don't need the left side because we already know the limits are 0 to 10. In fact, I'm going to go ahead and put a 10 over here. And when it says 5 right-hand rectangles, what I probably want to do pretty early into the problem is figure out the width of the rectangles. And the way we do that is figure out the width of the entire interval. That's 10 minus 0, which is 10. And you're going to divide it by 5. So we're going to get 10 over 5, which is 2 units. So that means if we just went, if that was 10 over there and we went 2, 4, 6, 8, 10. So now we have our intervals fairly well laid out. What I'd like to do is maybe switch colors here. We'll go with some green. When they say right rectangles, let me show you what that means. From 0 to 2, I would use the right side as the height, the wall height for that rectangle. I'm going to use the right side for this 2 to 4 region. I'm going to use the right side for this 4 to 6 region. I'm going to use the right side for this 6 to 8 region. And finally, I'm going to use the right side for this 8 to 10 region. Now, these are supposed to be equally spaced rectangles, and in effect, what we're doing is we're finding the area inside here, and the area inside here, and the area inside here. And it's fairly obvious from our picture, and we're not guessing at this. We do know that it's an over approximation. So we can tell that right now. So if they were to ask us a question about does it over or underestimate or over or under approximate the true area, remember the true area is the area underneath the curve. So that would be all of this really underneath the curve, like not over and not underestimating. So let me undo that red right there because I really want to do an approximation here. So to continue with this process, one thing you can do is you build a little table here. And that table keeps track of the y values. So I'm going to go x and f of x, and I'm going to basically go plug in all of those x values. And a lot of questions, they'll give it to you in this format. And what you're going to want to do is plug in 0, and then plug in 2, and so on. Remember, f of x is just the function that you're plugging into. That's this guy right here. So if you plug in a 0, you get a 0 squared times 3, which is 0 plus 2 is 2. Then you do it again. Let's say we go plug in like f of 2. You're going to get, let's see, that's 3 times 2 squared plus 2. 4 times 3 is 12. That should get us a 14. And then we continue like that. I'm going to go ahead and fill those values in right now because I've already got them worked out. And you can just follow my lead on those. Plug in a 6, you get a 110. Plug in an 8, the numbers are jumping up pretty high now. And then 10, that's an easy one. 10 squared is 100 times 3. That's 300 plus 2. So the idea here is we just found the height of each of these rectangles. Now, we got to be careful now. This first rectangle, in fact, let me get some different colors here. How about some pink? This first rectangle here, the height comes from using an x value of 2, not a 0. So I don't want to use this guy at all. I want to use the 14 for the height. And then, so my next rectangle would be using the height that comes with the x value of 4. Well, that would be a height of 50. And then we'll keep on going, maybe a different color here. So how about this height comes from using an x value of 6, and that gets us a height of 110. And so on. So we'll switch back, maybe back to some dark pink here. So use 8, that'll be the height, and then we'll switch back, maybe some dark blue here, so that one. We're going to use the x value of 10 for that one. So it turns out that these are your heights right here. These are the heights of the different rectangles. So really all we got to do is figure out what's the base and what's the height and multiply them. So I'm going to take this down here and say that that integral is approximately equal to, it's not equal to it, it's going to be approximation. It's going to be base times the height, and let's see, there's 1, 2, 3, 4, 5 rectangles. So I'll set up, let's see, that's 3, I'm going to run out of space here, and 4, and 5, sorry, I'm sneaking in there. Now the base is just how wide is the interval. We already said that. It's going to be 2 every single time. Next, we're going to go find the heights. Well, the heights, those are these guys in here. So we're going to take the 14, and we'll take the 50, then we'll take the 110, and we'll take the 194, and we'll take the 302, and we're just going to calculate all those. Now, one thing you'll notice is they all have a 2. Look, each pile has a 2 in it, right? So what we can do is we can factor out the 2, and then we could have just said what's 14 plus 50 plus 110 plus 194 plus 302. All right. So either way, one way or another, we're going to work this all out. We're going to get a final answer of 1,340 square units, whatever that is. They didn't give us inches or feet or anything like that. So technically we have our answer. We know it's an over approximation. If you go back to the original question, we could actually calculate that. We're not going to do it by hand. I will switch over to a calculator here so we can show that. But what we found is an area that's an over approximation. All this stuff up here, that's extra area above the curve. All right, let me switch over so you can see what I'm talking about. If I were to go to, this is an applet that we've got, and I can type in the actual function. So let me do that right now. I'm going to change that to a 3. Let's see, 3, and we're going to go x squared plus 2, and we want to go from 0 to 10. So let me go ahead and change those numbers. And they said we should use 5 rectangles. And we were using right rectangles, so I like the way that's set up right there. We have options though. You can see we have left, right, midpoint, minimum, and maximum. We'll never use those. We'll use the right. And then the color scheme is fine by me. And then we hit replot. And then what you can see here, you'll see the estimated area is that 1340 right here, and that's what we just found on paper. The actual area, if you integrated, find the antiderivative and plug in the 10 and plug in the 0 and subtract, the FTC, you're going to get the actual area was just 1020. So clearly, we can do this in a calculator, but we can also do them very easily by hand if they're easier problems. And what I mean by that is easier functions. I wanted to show you what happens if I switch this to a left rectangle. Let me go ahead and replot that. When I do a left rectangle, you'll notice that it's touching on the left side of each rectangle. The left wall of each rectangle is where you get the height from. So you can see the estimated area is now only 740 versus our 1,340. And the actual area does not change. It's still 1,020. So let's try midpoints. Here comes a midpoint. Now look at this. The estimated area is 1,010 versus the actual area of 1,020. That's a pretty good estimate. Now, if you look at the picture, you'll see there's some over approximating and some under approximating. There's some over, some gray area that's above the red curve. There's some white area that's below the red curve. So you could think of those as kind of canceling each other out. We did a little over and a little underestimating for every single one of these rectangles that we've drawn in here. All right. Now that is also dependent, that difference between the actual area and the estimated area, that is dependent on multiple things, one of them being the actual function that you choose to type in. So anyhow, that gives you kind of a decent idea. Now what happens if I take the number of rectangles up? That makes it more interesting too. Let's try that out. Let's make that 20 rectangles. And that looks good. And we'll replot. And look at this. We're still using midpoints, so it's definitely going to be the better of the three approximations, versus left and right. But look at the estimated area versus the actual area. Super, super close. I'm going to go ahead and switch it back to left. And we'll see that this is an under approximation, and now we're off by what, like 14, about 34 units. And if we go to right, it'll be an over approximation. And here we go, over approximation, and we're off by like 76.25 units. So clearly the midpoint is the way to go. However, it's not usually up to us. I mean, it'll be the question we'll ask, to use a left or a right or a midpoint or possibly a trapezoidal. We can take that number of triangles up. Let's go a little bit further. One more time on this. Oops, I just wanted to put a 0 on there. Let's do 200 rectangles. I think the applet can handle it. Here it comes. Whoa, look at that. And not only look at the picture, it's beautiful, but also look how accurate the estimated area is versus the actual area. Love it. So the idea of Riemann sums, you're adding up a finite number, a number that you can count, a number of rectangles that you can count. We added 5 of those rectangle areas. Then we changed it to 20 rectangles. Well, clearly doing 200 of those would be very, very time consuming for us, but a computer can do it quickly. A calculator can do it super quickly. And really, if you take a close look at the picture, you can see what's happening here. As you take the limit of that Riemann sum, if you let that number of rectangles go to infinity, you're basically getting the true actual area, which is the true definite integral value. All right, let's do one more thing on this, and then we will switch back and actually do more calculation. We have a calculator here, so if you could get your calculator out, feel free to pause the video if you need to. I'm going to go ahead and go to my y equals screen. Let me first clear my key press history. You'll notice down here at the bottom of the middle of the screen, you can see what buttons I'm pressing. If I press the y equals button, I've already got my equation in here, but I'm going to hit clear and just do it from scratch. I'm going to go 3x squared plus 2. And then I believe my window is already set up. I did that ahead of time. Let me go ahead and press the window so you can see what that is. I knew based on what I had seen from my table of values on paper that we were getting up to 302. So that's why I chose a y max of 350. But go ahead and change your window to match this. Don't worry about the weird stuff after the x res equals 1. Okay, so once you have that, you can see your graph, and that's nice. But what I wanted to point out is you can easily find those table values if you just hit trace and you type in the number 0, enter, 2, enter. There's your 14 in blue there. Type in the 4, enter. There's your 50 down here at the bottom of the graphing screen. Right? And you continue doing that, you'll easily get all those values that were in that table. Super quick way to do this. Now, it's maybe not as quick as what I'm about to show you, which is setting up the table. I'm going to go ahead and clear this mess, the keystrokes down there. We're going to go second, table set, which is window. Second window, you'll see second window down here on the bottom screen. Now you have some options. What do you want to set your table at? And I do like that it's at 0. If it said something else, I would clear it out, or I would just type in a 0. I want the table, hit the arrow down once. I want the table to go up by 2s though. Right? I hit enter, and I like these to stay on auto. The independent variable is the x, the dependent variable is the y. I want those to stay on auto, and watch this. Press second table, which is the graph button. Whoa, look at that. Beautiful. Now it goes forever and ever and ever. We could have, done something a little differently to stop at a certain point, but this is perfect. We've got the ones that we need all the way up to the 302, and then you could take those and you can write them back down over here on your table on paper. So there are all those numbers. All right. I think we have a pretty good understanding at this point of what a left, what a right, and what a midpoint is, sort of. Left and right. Let me talk briefly about the right on this. The right, when you look at these rectangles, you're going to go from 0 to 2, and then 2 to 4, and 4 to 6, and 6 to 8, and 8 to 10, and that's 5 loops. 1, 2, 3, 4, 5 loop-de-loos there. Now, if you look at that carefully, you've got the 0 and the 2. Those are both the x values at the base of that first rectangle. We need to choose the y value that's associated with the one on the right. Then we do it again from 2 to 4. That's this rectangle right here. We're going to choose the 4, which gets us a y value that's on the right. From 4 to 6, choose the 110 that's on the right. 6 to 8, choose the 194 on the right. 8 to 10, choose the 302 on the right. Notice what I've circled here like a madman. 1, 2, 3, 4, 5 rectangles heights, and we're not using the 2. Because again, that height of 2 came from a base x value of 0, which we are not using. All right. Had we been asked to do left rectangles, let me show you what that would look like. We would have done this, and this, and this, and this, and this. We would have used the left, the left, the left, the left, the left, and then not used the right, the 302. And of course, that would change our answer, because we would never have a 302 in the mix up here. And instead of our first triangle being base of 2, height of 14, it would have been base of 2, height of 2. All right, so we're going to go ahead and finish that video right there, and stay tuned for the next one. We'll get more in depth into how to calculate the rest of these.